Good evening, students. Today I am going to revise one chapter, that is magnetic effect of electric current. This chapter I am going to revise now. You listen very carefully. If you have any query while teaching, okay, you can ask me. Is my voice clear or not? Actually, this chapter we completed already, but again once I will revise and I will give some important key points. Okay, right. Even though while teaching, if you will get the doubt, you can ask me, right, students? Okay, going to start the class now. Our chapter name is, I'm going to start the chapter, that is magnetic effect of electric current. Okay, this chapter I am going to explain magnetic effect of electric current. Okay, right. Now in this first I am going to explain some Oersted experiment. What is Oersted experiment and what he did? Okay, the Oersted experiment is that, for example, if it is a Oersted experiment, what is Oersted experiment that I am going to explain? You listen very carefully. This Oersted experiment is that this is a current carrying wire. Okay, this is a straight current carrying wire. Beside of this current carrying wire, he kept one magnetic compass. Do you know magnetic compass? What is a magnetic compass? Magnetic compass consists a tiny magnet, small magnet, that is pivoted over a pin, that is kept near the current carrying wire. At that moment, what he observed, and while doing some other experiment, he kept like that. At that moment, he observed one thing, that this magnetic compass needle, this is the compass needle. Okay, compass needle. What is this compass needle? Okay, why the compass needle is deflected? Okay, when magnetic compass needle, magnetic compass needle deflected when it is placed near the current carrying conductor, near the current carrying conductor. Before this observation, magnetism is different from electricity. Okay, magnetism is the property of produced by the magnet. Electricity is the current produced due to the flow of charges. These are the two different phenomena. But after observing this Oersted experiment, Oersted is the name of the scientist, he observed this one, that he kept the magnetic compass near the current carrying wire. When magnetic compass means what? Tiny magnet placed over a pin, pivoted over a pin. You see here this figure like this. For example, this is a pin. Okay, okay, this is a tip. At the tip we kept the magnet. The magnet is free to rotate in the horizontal plane like this. Then this is kept in a non-magnetic box. Okay, right. Then this compass pointer, this needle is a magnet, and a magnet placed over a tip. It is free to rotate in horizontal plane. And this is a tiny magnet, small magnet. This is deflected when it is kept near the current carrying conductor. Then by this he gave the relation between the magnetism and electricity, and he gave one conclusion that a current carrying wire also produces the magnetic field. Generally, the magnetic field produced by the magnet, but the current carrying wire also produces the magnetic field. Then he gave the conclusion what? current carrying wire produces magnetic field around it. Current carrying wire generally due to current electric field should be produced, but current carrying wire produces magnetic field. Okay, in that magnetic field, if any other magnet or compass is there, then the compass needle is nothing but any magnet that will be deflected by the magnetic field that produced around the current carrying wire conductor, and this leads to relate electricity with the magnetism. After invention of this, electricity and magnetism are related. Okay, and they produced the current from magnetic property also. Okay, from election of current generated by the direction of the magnetic field generated around the current carrying conductor can be given by the right hand thumb rule. Okay, I will write the heading as right hand thumb rule only. Right, what is the use of this right hand thumb rule? The right hand thumb rule is right hand thumb rule. Right hand thumb rule. What is this right hand thumb rule? Okay, the right hand thumb rule is that the direction of magnetic field produced by current carrying conductor, produced by current carrying conductor, given by right hand thumb rule. Okay, what is this rule? How we can find out the direction of magnetic field? What is magnetic field? Do you know this one? Let us continue. Right hand thumb rule is that the current carrying wire is held in the current wire held in right hand. So you have to hold in the right hand in such a way that if it is the current carrying wire, okay, you have to hold the current carrying wire with your right hand. Okay, you have to hold the right hand with the right hand in such a way that the thumb shows the direction of the current, and the curled fingers indicates the direction of the magnetic field. This is the right hand, you see here. Now here this thumb is indicating the direction of the current. Direction of the current is indicated with the thumb. Okay, thumb shows the direction of the current, and the curled fingers are showing like this, right? And the curled fingers indicates the direction of current, direction of magnetic field. Direction of the magnetic field is given by curled fingers. Okay, now what we have to do it here? Thumb shows the thumb shows the direction of current. Thumb shows the direction of current. Then curled fingers indicates the direction of magnetic field line, direction of magnetic field produced around the current carrying conductor. Understood? This is about right hand rule. Any query, students, till now? Any doubt? Right. Let us continue now. Now I am going to erase this. Next, magnetic field lines produced by the bar magnet. So what is magnetic field? And magnetic field means the region around the magnet, the region around the magnet, the region around the magnet in which its effect is exist is called as magnetic field. Magnetic field is the region around the magnet. In that region, that magnet effect is exist. That magnetic basic properties I am going to explain. Properties of magnet. Properties of magnet. Basic properties. Okay, you see here, for example, this is a bar magnet. This has north and this is south. Every magnet has the two poles. Okay. Every magnet has two poles. What are they? North and south poles. And they observed that like poles are repel with each other. Like poles are repel with each other. Like poles are repel with each other. And unlike poles are attract with each other. Unlike poles attract with each other. Now, this is a magnet. This magnet effect is exist up to particular region around it. For example, in this region, the magnet effect is exist. If any magnetic substance are placed or other magnets are placed in this region, that is attracted by this one. Okay, right? This pin is attracted by this one. If we place this pin outside of this region, then it cannot be attracted. That means this magnet effect, its attraction force exists up to particular region. That region is called as the magnetic field. The strength of the magnetic field is given by the some properties. There is a magnetic field line. What is the magnetic field? Strength of the magnetic field also called as magnetic field simply. What is magnetic field line? Magnetic field lines. Magnetic field lines means it is the path traced by unit north pole kept at a point, kept at a point in magnetic field is called as magnetic field line. This is about magnetic field line, right? Okay. What is this magnetic field line? The path traced by, I am telling it here, the path traced by unit north pole kept at a point in the magnetic field is called as the magnetic field lines. What is this path traced by unit north pole? Okay, path traced by unit north pole means, for example, this is a north pole of the bar magnet. This is the north pole of the bar magnet, and this is the south pole of the bar magnet. If we keep the unit north pole at here, this north repelled by the north, and this south attracts the north. Like poles are repel with each other. North, north repel, north, south are attracted. If you keep the unit north pole at here, this unit north pole is repelled by this north of the bar magnet and attracted by the south. That's why it will follow this path. It will go like this. we place the unit north pole at here, okay, that unit north pole will follow like this. It will go along this path, like this it will travel, okay, right. This is the path along which the unit north pole travel. This path is called as the field line, okay. This is the field line. And the next another field line we will take. This is also field line. These are the magnetic field lines, okay. The magnetic field lines outside of the magnet, they starts at the north and ends at the south. Look at here. Outside of the magnet, they starts at the north and moves toward the south. And inside the magnet, they will go from south to north. South to north. Okay? Right. This is about magnetic field lines. And now, properties of magnetic field lines. What are the uses of the properties of? These are the imaginary curves. Okay? They cannot appear for that. These are imaginary, they cannot appear around the magnet. These are imaginary closed curves. These are imaginary closed curves. How we are telling closed? Because outside they goes from north to south, inside they will go from south to north. Means this is closed curve, right? Outside their direction from outside of the magnet, outside of magnet, these lines starts at north and ends at the south. Okay, outside of the magnet, these lines moves from north to south. But inside the magnet, their direction from inside the magnet, their direction from south to north, right? South to north. And the second property is that if we draw the tangent at any point on the field line, this is a field line, okay, this is a field line, magnetic field line. This field line, on the field line, if we draw the tangent at a particular point, like this, at this point I want to draw the tangent. Tangent means but it's a line, it touches at one point. This tangent gives the direction of the magnetic field, okay, right. The tangent drawn at a point, the tangent drawn at a point on the magnetic field line, tangent drawn at a point on the magnetic field line gives the direction of magnetic field, gives the direction of magnetic field at a point, okay, right. And now third one is the very important. Magnetic field lines do not intersect with each other. Magnetic field lines do not intersect with each other. They cannot cut with each other. Why they cannot intersect with each other? Because if they intersect, what happens? They intersect at intersecting point. Compass pointer should show two directions. Compass pointer or the compass needle compass needle should show two directions, but it is not possible. Compass needle should show two directions, but it is not possible. Okay, right. You take the screenshot and note it. Right. Compass needle should show two directions. At single point, it should show two directions, but it is not possible. Right. For example, here like this, two field lines are intersecting with each other. This field line is like this there, and this field line is like this there. We can draw for this line tangent like this. This side magnetic field is there. This side compass pointer should show. And for this also, if you draw, this is the direction. That means at single point, we are getting the two tangents. Two tangents means two fields. Field can be denoted with D, two directions. But at single point, the field has only one direction. That's why the field lines do not intersect with each other. Okay, right. Understood, students? If you have any query, write in the chat box. Any doubt? Next important point I am going to explain. That is, any doubt, students? Write in the chat box. Okay, I will erase this one. Now, how magnetic field produced by the straight wire, on what factors it will depends. Magnetic field produced by, okay Savan, good. Magnetic field produced by, first one straight current carrying wire. Okay, first one is a straight current carrying wire. Straight current carrying wire. And the second one is magnetic field produced by the circular loop, circular current loop. And C is the magnetic field produced by the solenoid. Then about these three we are going to discuss. On what factors the magnetic field produced by these will depends. Okay. The first one is a straight current carrying wire. This is a straight current carrying wire. The magnetic field produced by the straight current carrying wire, on what factors it depends and how the field pattern will be there. We will place one paper at here like this. Then magnetic field pattern we can draw it here. How the field lines will be there. You see here the field lines will be like this there in circle shape around the current carrying wire. In circle shape they are there. The field lines will be in the circle shape. What is the direction of the field? Direction of the field lines will be like this there. Okay, the current is in upward direction. You see here, you have according to find the direction of the magnetic field produced around the current carrying wire. Then the current carrying wire is this current carrying wire. This pen, this tip is the direction of the current. You have to hold the current carrying wire in the right hand in such a way that the tip shows the direction of the current. Thumb shows the direction of the current. Okay, the tip is the direction of the current. Thumb also direction of the current. The curled fingers is indicating the direction of the magnetic field. This curled fingers is coming like this, right? They are coming like this, like this, like this, right? This is anti-clockwise. Then we can draw the field line directions like this, right? And this is the field line. Okay, right. Like this we have to draw the field lines, draw the field lines due to the state current carrying wire. On what factors this field lines depends? Magnetic field, magnetic field produced by the straight wire depends upon the current. Okay, this magnetic field we write as B. Magnetic field depends upon the current. If large current passes, the field will be more and compass undergoes more and more deflection. Okay, this is the first point. And the magnetic field also depends upon, magnetic field depends inversely proportional to distance. Where smaller is the distance. If you will go away from the current wire, distance from the wire, okay, if you will go far away from the wire, then if you will go far away from the wire, then the field will be decreases. For example, we will take the 2 points at here. Okay, if current is more at here, then the field is more, right? Field is more, more magnetic field is generates. If distance is more, then the field is less. What is the meaning of this one, right? For example, this B is the magnetic field. Magnetic field is more means more force act on any substance, magnetic substance which is placed near the current carrying wire. For example, if you take the 2 points, this is a current carrying wire. I am selecting the 2 points at these fields are B1 and B2. Can you tell whether B1 greater than B2 or B2 greater than B1 or B1 equal to B2? Okay, you can tell from here. The first point distance is R1, second point distance is R2. When you will go far away from the current carrying wire, the field is decreases. From this we can write as, can anyone write in the chat box? I will leave. Okay, let us go for the, you give the answer. Okay, and next circular current carrying loop. Circular current carrying loop. Magnetic field produced by the circular current carrying loop I am going to explain. And for this again we will take one plane of paper. And here this is a current carrying wire. For example, the current carrying wire is in circle shape like this. The current passes. Now, for example, this is a current carrying wire. This is a positive terminal. This is a negative terminal connecting to the battery. The current flows like this, right? Current flows like this. I want to draw the field lines at here. How the field lines will be there due to this current carrying wire? The field lines direction. Okay, we have to use the right hand rule at here. Right hand rule. Then according to the right hand rule, we have to do one thing, that in this current is entering, in this current is entering, in this current is leaving. When the current is leaving it here, then how the field lines will be there? Current is leaving means on the left side, they are drawing the left side here. Here when current is upward, okay, current is upward. Then thumb shows the direction of the current. Curled fingers is indicating like this, right? That means the current will be of magnetic field lines in the circle shape, and they will be like this. In this current is entering. Current is entering means, okay, first we draw the direction of the current also, right? What is the direction of this one? The direction of this field lines generated around this. Okay, current is upward. Current is upward in this. You see this current is upward. When the current is upward, what about the field lines? Field lines are in anti-clockwise, right? Then they will appear like this. This is the direction of the field line. Direction of the field lines. Okay. Similarly, in this, the current is entering. In the right side, if you will see, current is down. Downward means thumb should shows the direction of the current. Current should be downward. And field lines will be like this, clockwise. Right? They are in circle shape. This is the field line pattern. Okay, they are in circle shape. Field lines are in the circle shape. Then the field lines are in the clockwise direction. Like this, it will be there. Right? This is the direction of the magnetic field pattern. Magnetic field pattern produced due to the circular current carrying wire. This you should remember. This in the uh, textbook also you will find the diagram. Okay, if it is this is a current carrying wire. I want the field at the center. Okay, field magnetic field at the center. Around the current carrying wire, field will be produced. On what factors the magnetic field depends? Okay, the magnetic field denoted magnetic field means on what factors the magnetic field depends. The magnetic field due to this loop, okay, it is depends upon the magnetic field depends upon the number of turns. Number of turns. Okay, if more turns are there like this, like this, like this, like this, right? Then field will be more. And field is directly proportional to current. In everywhere the field is proportional to current. If current is more, the more field is there. And field is inversely proportional to this. I is the current at here. Okay, and field is inversely proportional to r, where r is the radius at here. R is the radius. If radius is more, the field is less. If current is more, the field is more. In the directly proportional, if one is more, other is more. In inversely proportional, if one is more, other is less. This is the magnetic field pattern due to circular current carrying loop. This is circular current carrying loop. This is a straight current carrying wire. Actually, one thing, for the solenoid also we are going to draw the magnetic field line. What is a solenoid? Solenoid means a current carrying wire. Okay, an insulated current carrying wire. An insulated copper wire wound around a cylinder is called as solenoid. Magnetic field means what? Okay, if the field is more, the field is strong means, and if you place any magnetic substance, then the more force act on that. Okay, right. Insulated copper wire wound around a cylinder, that is called as solenoid. Let us see here. This is a solenoid. Okay, I will draw the diagram of the solenoid. You listen very carefully. This is a hollow cylinder. Okay, so we have to draw the magnetic field pattern also. Little bit down I will draw. Okay, right. This is a solenoid. Now the magnetic field pattern due to the solenoid we will draw like this. This is the field lines. These are the field lines. Sorry, not the field lines. It's a current carrying wire. The current carrying wire wound around a cylinder. Okay, right? The current carrying wire. The current direction is this one. This is the direction of the current. The current is flowing like this, like this, like this, and then finally This is a wire wound over a cylinder. Now this current carrying wire, insulated copper wire, okay, current wire, and this one end will act as the north pole and other end will act as the south pole, okay, and this is equivalent to the solenoid is equivalent to the magnet. Solenoid, current carrying solenoid is equal to magnet. This is equal to magnet. The field length generated by this one is exactly similar to the field lines generated by the magnet. They will start at the north outside and they will go to the south. Inside they will go from south to north like this. Because the magnet, the solenoid is equal to magnet, that's why the field lines also similar to the magnet. That's all very easy, right? Students, are you understanding? Any query? If you have any doubts, you can ask me. Outside, they will start at the north and ends at the south. Okay, the field lines. These are the magnetic field lines generated by the solenoid. The solenoid is exactly equivalent to the bar magnet. Now let us see on what factors the magnetic field depends. Magnetic field is uniform inside the solenoid. Magnetic field is uniform. Uniform means constant. Field uniform inside, okay, inside solenoid. And the field depends upon some factors. That again the field is proportional to current. If more current passes, more field. If field is directly proportional to the number of turns and the field is inversely proportional to the length. And if this one is what field is inversely proportional to the length. If length of the solenoid is more, the field is less. This is the L is the length of the solenoid, I is the current, okay. And what is this field line? Field line, okay, these are imaginary, right? If length is more, the field is less. If number of turns is more, and if solenoid is filled with the soft iron, okay, then field will be increases. It also depends upon the medium, okay. And solenoid is nothing but this is you take the plastic pipe and over that insulated copper wire is wounded, that is called as the solenoid, okay. And that field is depends upon the current also. Field depends upon number of turns also. Field depends upon length also, okay. You in exam they will ask, if current increases what happens to the field? If current double, what happens to the field? Current double means field will be double. If length double means field become half. Because inversely proportional means decreases, okay. Directly proportional means in the same amount increases, right? And if soft iron kept in middle of solenoid, field increases, okay. Field increases, right? This is about magnetic field due to solenoid, okay, right. And now magnetic field pattern we discussed. Next topic I am going to explain, that is the force on current carrying wire. Force on current carrying wire in the magnetic field. Force on current carrying wire in the magnetic field. You take the screenshot, and in the textbook also it is there, line to line you have to read. You understood everything. Once again, I am revising everything. Okay, right. Let us go for this. Next topic is the force on current carrying wire in the magnetic field. Okay, next topic is force on current carrying wire. Force on current carrying wire in the magnetic field. Force on current carrying wire in the magnetic field. If we place any current carrying wire in the magnetic field, on that wire force will act. That force on what factors it depends. Okay, right. For example, this is a current carrying wire. This is a current carrying wire. This current carrying wire is placed in the magnetic field. What is magnetic field? Okay, this is the, for example, north pole of the magnet. This is the south pole of the magnet. Between the two poles of the magnet, I kept one wire. Okay, you see here, right? The magnetic field direction, you remember it. That is the field is direction is, this is the current carrying wire. This is the current carrying wire. The current is right side. The field direction is from north to south. Remember, away from the north and towards the south. This is the direction of the field. Field direction is from north to south. Magnetic field direction from the is north. Field direction, magnetic field is from north to south, away from the north towards the south. Okay, magnetic field means what? Force field means magnetic field. Magnetic field means the region around the magnet, its effect. Magnetic effect exists up to particular region, that is called as the magnetic field. The strength of the magnetic field, how much force acting. Okay, field means force per unit pole strength. For example, if you keep any another north pole here, this north pole repelled by the north. If more repulsion is there, then more field is there. That means field is the force. Okay, how much force is acting, strength of the field is, it is a magnetic field. Magnetic field is from north to south. Now, force on current carrying wire in the magnetic field we want to find out. For that, what we have to do it here? Then we have to place the one current carrying wire in the magnetic field. For example, this is a current carrying wire. Okay, that I kept it here. This is a current carrying wire. Okay, this is a current carrying wire. The current is right side. It is flowing. Okay, current is flowing right side. The magnetic field is downward at here. Magnetic field is downward. Okay, the current is right side. Then I want one thing, that what is the direction of the force and who will give the force. Whenever this current carrying wire, it is kept near the, in the magnetic field near the magnet, then this current carrying wire experiences the force, and this current carrying wire will be deflects, right? That is experimentally observed, an experiment also there. And what factors this force will depends? Force on current carrying wire. Force on current carrying wire. On what factors it depends? The force depends upon current, force depends upon the current, and force depends upon the length. Okay, force depends upon the current, force depends upon the length, force depends upon the magnetic field. These are the factors on which the force depends. Okay, if more current passes through the wire, then more force will act. More length is there, more force acts. More field is there, more force acts. These are the factors on which the force on current carrying wire depends. Who will give the direction of the force? How we will give the direction of the force? Direction of force is given by one rule. What is that? Direction of force is given by, what is that? Fleming. Fleming rule. Okay, That is a Fleming left hand rule. Fleming left hand rule is used to give the direction of current. According to the Fleming left hand rule, then how it will give the direction of the magnetic field, I will explain. Now, first one is the Fleming left hand rule. Fleming left hand rule is used to know the direction of the force on the current carrying wire. Just you take one wire, current carrying wire, you take one magnet and kept near the wire. Okay, for example, this is a current carrying wire. You take one magnet near to current carrying wire. This current carrying wire on current carrying wire force acts and this can able to deflect. It can move. Okay, this is a current carrying wire and this is a magnet. When magnet is kept near the current carrying wire, this current on the current carrying wire force will act and it will deflect. Why force is acting? Because current carrying wire is generating around the current carrying wire magnetic field produces. This magnet also magnetic field produces. These two magnetic fields either they may attract or they may repel due to that the current carrying wire kept in the magnetic field experiences the force and it will deflect, right? And Fleming left hand rule is used to know the direction of the magnetic field. Then what is the Fleming left hand rule? According to the Fleming left hand rule, stretch the stretch left hand thumb, forefinger and central finger mutually perpendicular to each other. How we have to stretch? They should be mutually perpendicular to each other. Perpendicular to each other. We have to stretch like this. When we will stretch them perpendicular to each other, okay, adjust the forefinger in the direction of magnetic field, forefinger in the direction of magnetic field and central finger in the direction of current, central finger in the direction of current. Then thumb shows the direction of force on current carrying wire. Direction of force on current carrying wire. Current carrying wire. Okay, I will simplify it and I will write here. Okay, you take the screenshot and note it. What is B in this? B is the magnetic field. Okay, B is the magnetic field. B is the magnetic field. Right. What we have to do it here? You have to stretch the forefinger. You see here, this is the left hand. Okay, left hand. You have to stretch like this. Okay, like this. Left hand, forefinger, central finger, thumb. Forefinger, central finger, thumb. They should be mutually perpendicular to each other like this. Okay, you can move with the wrist, but you should not move the fingers. These two are perpendicular to each other. These two are perpendicular to each other. These two are perpendicular to each other, right? All are perpendicular to each other. Adjust the forefinger in the direction of the magnetic field. Adjust the forefinger in the direction of the magnetic field. How we know the direction of the magnetic field? The magnetic field is away from the north and towards the south. And then adjust the central finger in the direction of the current. Central finger in the direction of current. is the current direction. Then the thumb indicates the direction of the force. Direction of the force. Okay. What do we have to do it here? Right? Forefinger should be adjusted in the direction of the magnetic field. Forefinger adjusted in the direction of magnetic field. And forefinger is adjusted in the direction of the magnetic field. Yes, I had according to the revised syllabus I am teaching, and according to revised syllabus, only one topic is removed in this chapter. That topic is electric generator, AC generator. One topic is there. Only last topic and domestic uh, electric circuit. Okay, that just two topics are removed in this chapter. Last two topics, except that all the topics are present. Okay, forefinger in the direction of the magnetic field, and central finger is in the direction of the current. Then our thumb shows the direction of the force. Thumb shows the direction of the force. What is the use of the Fleming left hand rule? It is used to know the Fleming left hand rule used to know. What is the use of this one? Fleming left hand rule used to know the direction of force. Used to know the direction of force on wire. Direction of force on current carrying wire. Right? Okay. Now let us. I will give one example for this. Okay. I will give one example. You try for it to know the direction of the current. For example, the current is current carrying wire. Okay, current carrying wire. This is the current carrying wire. The current carrying wire is held in like this: north, south, east, west. Current carrying wire is from east to west. That is considered current is flowing from west to east. Current is flowing from west to east. So we applied the magnetic field. The earth magnetic field is from like this. This is the direction of the earth magnetic field, south to north. Okay, this is the earth magnetic field. This is the current carrying wire. Then how to know the direction of the magnetic field? Okay, right? Or otherwise, simply I will give one thing, right? Okay, you take this is a current carrying wire. Current is like this there. We kept the north pole at here and south pole at here. The direction of the magnetic field is downward. This is the direction of the current. Current is right side. What is the force on this one? Just you adjust the current direction. You draw this on the paper. On paper, you adjust the forefinger in the direction of the magnetic field. Field is downward like this. Okay. Current should central finger should be in the direction of the current. Okay, like this. Central finger is right side. Then the thumb is in inside like this. Like this, it is there. That we can say that inward. Inward. Like this, we can find out the force. Okay. Find the direction of force. If you join lately, then you can give the attendance. According to the CBSE syllabus, I am teaching Vikram. Who is present now? In 2 members are present, 4 members are there. In the last, those who are present, give your names. I will note. सावन आप प्रेजेंट है ना अभी? और कौन कौन है रनिंग में? Write in the chat box who is present now. 4 members are there.